Hello, my name is Ashley Arcidiacono, and I'm a member of the Hansen Research Group at Florida State University. Today, I'll be sharing with you our newest publication in the Journal of Photochemistry and Photobiology, titled Inhibited Interlayer Electron Transfer and Metal Ion Linked Multilayers on Mesoporous Metal Oxide Films. We're joined in this publication by Professor Michael Roper from Florida State University. Initially, our goal generate a self-assembled metal ion linked multilayer, which included a ruthenium-based dye, N3. It was then linked to an electron donor, our cobalt in this instance, so as to more rapidly regenerate the ground state of our N3 dye. We hoped that the geometric restriction of the molecules would allow for us to slow the back energy transfer as well as the recombination, which are typical loss pathways in dye-sensitized solar cells. Our first step was to generate the bilayer. Typically, we monitor loading with UV visible spectroscopy. However, in this instance, the loading of the molecules was obstructed by the onset of TiO2 absorption. So instead, we turned to ICP-MS, inductively coupled plasma mass spectrometry, where we first assembled the bilayer. We would then desorb the bilayer from the surface and measure the concentration of the metal centers. Using this technique, we were able to determine the final loading ratio of 10 to 10 to 1 of N3 to zinc to cobalt. We then incorporated the bilayer into a device architecture where we saw that the TiO2 N3 devices exhibited the highest overall performance, with the bilayer films giving us the lowest performance in every device metric. When trying to understand where this behavior came from, we looked at electrical impedance spectroscopy, and we found that the bilayer actually has the highest resistance to recombination out of all of our devices. However, this small gain is offset by all of the other loss pathways in the cell. To investigate regeneration, we used transient absorption spectroscopy, and we found that overall, cobalt is largely inert in our bilayer structure, and that the excited state quenching and the cobalt to N3 cation electron transfer is slower than excited state decay and recombination, respectively. So overall, the steric bulk of the cobalt may be the reason for the slowed regeneration rate that we see. When trying to investigate perhaps why we saw this slowed electron transfer, we turned to Marcus theory. We saw that, in fact, in solution, cobalt is able to regenerate the ground state of N3 rapidly. However, when incorporated into the bilayer assembly, we effectively shut off the electron transfer. We believe this happens because we effectively double the distance between our ruthenium and our cobalt metal centers when we incorporate it into the bilayer. Using Marcus theory, we were then able to estimate an attenuation coefficient between 0.25 and 0.5 reciprocal angstroms, which is similarly conductive to phenyl bridging systems. Overall, we were able to use an N3 dye and a cobalt polypyridyl electron donor in a multilayer assembly. We introduced ICP-MS as a new technique to quantify surface loading of spectroscopically obscured molecules. We found that incorporating cobalt decreased the overall dye-sensitized solar cell performance. We found that excited state quenching in cobalt to N3 plus electron transfer is slower than excited state decay and recombination. And then lastly, we found that cobalt can readily electron transfer to the N3 ground state in solution, but the multi-layer assembly, or the ion-linked bilayer, allows us to impose enough of a geometric restriction that we effectively turn this electron transfer off. So although we were not able to generate an effective dye-sensitized solar cell, this architecture may be useful in the future for systems where you intend to translate things or communicate things like electron spin or dipole moment, and not necessarily an electron itself. If you'd like to learn more about this publication, please visit the DOI at the bottom of the screen and follow us at Hansen FSU on Twitter and Instagram. Thank you.